Apache Spark is a famous open-source data processing engine designed for large-scale data analytics, which can handle massive datasets efficiently. It provides a unified framework for batch processing, real-time data streaming, machine learning, and interactive queries, making it a versatile tool for data engineers. In Uber, Spark primary computing engine, supporting operations like rides, Uber Eats, or maps. Uber's Spark usage has grown exponentially, running on over 10,000 production nodes and processing hundreds of petabytes of data daily. Operating Spark at Uber's scale presents challenges despite its benefits, especially with data transfers between job stages, famously known as shuffle. In this video, we will discover how Uber resolved the shuffle challenge when they operated Apache Spark on a large scale. But first, let's have a look at the original Spark shuffle operation. Spark Shuffler has two sets of tasks, map and reduce. The first produces the shuffle data, and the latter consumes it. In Spark's Task Exchange shuffles data using pull models. The map tasks write the shuffle data to the local disk. Then, reduce tasks reach multiple map tasks to pull that data. Let's examine the shuffle write state closely. Uber's initial Spark Shuffle implementation lets map tasks write shuffle data to the local disk. First, they write data to a memory buffer. When the buffer is full, they spill data to disk temporary files. Later, they merge all spill files into the final shuffle files. In many cases, they must perform multiple disk operations, read and write, on the spill files, which incurs latency. In the shuffle read stage, the reduce tasks talk to the shuffle services running on mapper hosts to get the shuffle partition data. When the shuffle service receives the request, it looks up the index file to locate the desired data for the reducer, and returns it. The reduce task will pull the data into the memory buffer and then generate the iterator for the reducer process to consume. This process is inefficient because the task has to ask many mapper hosts to get a partition's data because a single map task can output data from multiple partitions. For example, if a reducer wants to consume data from partition 1, it has to reach many map hosts to collect the data. This can incur network overhead and make the mapper hosts do a lot of disk operations. Moreover, when Uber operates Spark Shuffle at a super large scale, there have been multiple challenges. First, the hardware reliability. Due to the large volumes of shuffle data being written to the SSD daily, Uber disks were worn out faster than the initial design. Instead of being sustained for 3 years, the disk at Uber wears out in 6 months. Second, the noisy neighbor issue. Because a single map host can have multiple applications, if there is an application that writes more significant shuffle data, it will potentially take up all the disk space volume in the machine, which causes other applications on this machine to fail due to disk-full exceptions. Third, the shuffle service unreliability. Uber used the shuffle service in Yarn and Mesos for Spark. They often experienced the shuffle service being unavailable in a set of nodes. So, how did Uber solve all of these problems? Realizing the primary root cause is the local shuffle data writing, Uber decided to move shuffle data away from the mapper host and store it remotely on dedicated servers. After many experiments, they introduced the RSS, which stands for Remote Shuffle Service. Let's continue with the RSS components. First, the RSS servers. These servers store the shuffle data during the Spark execution process. Second, the Shuffle Manager. It is the component that implements Spark's Shuffle Manager interface and is responsible for selecting and tracking remote shuffle servers and handling data uploads and downloads. Each Spark host has a Shuffle Manager. Third, the Service Registry. This component maintains a list of available RSS servers. Uber uses Zookeeper as a service registry. Each RSS server keeps a long-running connection with the Zookeeper to update its status periodically. Next, we'll explore how the Spark execution process differs from the original flow when using RSS. First, the Spark driver does shuffle registration, connects with the service registry, gets a list of available servers, does some checks, and picks some of them. Second, the driver encodes the RSS server list to the shuffle handle. The Spark machine passes this information on to map reduce tasks. Next, the map tasks send output shuffle to the RSS servers, and data from the same partition will be routed to the same server. Finally, Reduced tasks only need to fetch shuffle data from a single server with its desired partition. A significant change here is that the mapper would write data from the same partition to the unique RSS server. So the reducer would only need to fetch data from one RSS server instead of directly communicating to multiple map servers in the original solution. Uber could mitigate the Spark job latencies on the remote shuffle server by doing this. Next, let's see some benefits that RSS brings to the table. First, the hardware reliability. The disk lifecycle now lasts longer than 12 times than the original Spark shuffle solution. Second, the application reliability. The failure of the Spark jobs was reduced significantly. Third, the scalability. RSS can easily scale to handle large shuffles by getting more RSS servers involved. Before we end this video, let's wrap things up. The large scale of Spark shuffle data causes Uber some trouble. Uber manages shuffle data remotely using Remote Shuffle Service, RSS, to address this. RSS's main idea is to let the Spark executor send shuffle data from the map task to the remote server. Then, the reducer will fetch data from there. Moreover, Uber had to reverse the map-reduce paradigm from the original to make the solution more efficient. Thank you for getting this far. By the way, I'm currently the author of Vutrin's newsletter. If you want to receive in-depth data and software engineering content, subscribe here. It's free. Please like and subscribe if you enjoy this video. It will greatly motivate me. Now it's time to say goodbye. See you next time.